In this video, I will be looking at the math behind Gabriel's horn paradox, or painter's paradox as it's sometimes referred to, and then comparing that math with a real-world example. Gabriel's horn, or the painter's paradox, starts with the function y equals 1 over x. If we were to graph y equals 1 over x, it would look something like this. It would start high on the x-axis, on the y-axis, and then sweep down, and then taper. And while we let x go to infinity, this curve will never actually reach the x-axis. It gets very close, but it never reaches. In Gabriel's horn, the shape Gabriel's horn is formed by rotating this line around the x-axis to form what we call a surface of revolution. So we're going to, for this example, we're going to truncate our graph here at x equals 1. And then we're going to rotate the line from x equals 1 to infinity. We're going to rotate this line around the x-axis. This will give us a shape that looks very much like a horn, or a vuvuzela, if you're a soccer fan. It'll look something like this. Excuse my rudimentary drawing. And this horn will taper forever and ever, but never actually meet. So the first thing we want to do for this problem is find the volume of this shape. Because the whole premise behind Gabriel's horn and the painter's paradox is that this shape here, formed by y equals 1 over x, has a finite volume but an infinite surface area. So meaning that you could, in theory, fill it with paint, but yet never paint the outside of it. So that's what we're trying to prove here today. So we'll start with the volume of this shape. So to find the volume, firstly, we're going to just look at a cross section of this horn. We'll just draw ours here. So if we were to find the volume, we'll treat this like it were a short cylinder, because it is in 3 dimensions. It's a circle and it has some height to it, which we would call a cylinder. And this is essentially, we're treating this like Riemann sums from Calculus 1. And we're taking such a small rectangle here that we're just going to act like this portion here is a straight line because it's infinitesimally small. So we'll just treat this like a cylinder, and then we'll find the volume of this cylinder and then the volume of many cylinders and sum those together through an integral. So to find the volume of a cylinder, the first thing we need to know is the area of the circular face of that cylinder. And the area of a circle is just pi squared. We know that. So from the surface area of the circle, which is on the face of this cylinder, pi r squared. And then we're going to multiply that times the height or the width of this cylinder, this width here. And we're going to call this width dx. And by doing this, we'll be able to form an integral. So our initial integral will look something like this. The integral from 1, because we truncated our graph here at 1, and we're going to x equals infinity. So the integral from 1 to infinity of pi r squared times our dx, our width, our height there. So, times dx. So, we do know that we need this radius here, but what is this radius? If we were to cut this horn down the middle, what is this radius here? Well, this radius is defined by our initial function y equals 1 over x, because this radius is just the distance between the x-axis and the top of that curve. So we can substitute our initial function 1 over x into our integral. So we're going to rewrite this integral again up here. So our new integral will look like this. The integral from 1 to infinity, and we're going to remove this pi and put it on the outside of the integral as it's a constant. So pi times the integral of r squared. So as we discussed, our radius is our initial function 1 over x. So we're going to square our initial function, and that will give us 1 over x squared times our dx, our width here. And when we evaluate this integral, what we'll come out with is pi times, and integrating 1 over x squared is just x to the negative 2. Integrating that, we get 1 over at negative 1 over x, evaluated from 1 to infinity. Evaluating these two values, we start with infinity. So plugging in infinity, we get negative 1 over infinity, which is 0. 1 over infinity yields us a 0. So this is pi times 0, and then we're going to subtract our bottom value. So we plug in 1, we get negative 1 over 1, so negative 1. So subtracting negative 1, we're going to add 1. So we get 0 plus 1 from that definite integral. And multiplying this value, pi times 1, we get that our volume is equal to exactly pi units. Now, it didn't really matter that that came out to pi. I mean, it's pretty cool that it did, but we were just trying to prove that the volume of this is a finite number, and pi certainly is a finite number. So now, our next step is to prove that this same horn that has a finite volume has an infinite surface area. So I'm going to redraw this horn over here. Again, this tapers forever and ever and never meets. And so this time we're also going to take a look at another cross section here. But this time, instead of looking at the volume of this, we're looking at the surface area all the way around this circular horn. And if we were to draw this section by itself just down here, we would get something that looks vaguely like this. We'll have our two slants on the top and the bottom, and our two straight faces on the front. And furthermore, if we were to take this sliver of this horn and flatten it out, if we were to just cut it, if this were a piece of paper, we were to just cut it and lay it flat, we would get a shape that looks like this. So you can see how if we were to take these two ends and push them together, we would get this conical shape, this cross section of this horn. And this is what's known as a frustum, a conical frustum. And to find the surface area of a conical frustum, there is a formula, and through heavy algebra that I'm not capable of working, the formula comes out that the surface area of a frustum, you need two lengths. You need this length here, and we're going to call that A, and you're going to need this length here, which we're going to call B. And if we were to go back to our initial shape here and think in our cross section here, and think what A and B, what values these two letters correspond to, well, B is going to be our slant here, our short side, our slant. And A is just going to be the circumference around our horn. So this is just, if we were to curl this back up, we would just get a circle. And this circle, this length A is the circumference of that circle. So the circumference of a circle is just 2 pi r. So we know that A equals 2 pi r. And we know from our previous steps here that our radius here is defined by our initial function 1 over x. So we get A is equal to 2 pi times 1 over x, because like we said, this is our initial value, or this is our initial function which defines our radius. And this b length is an interesting component, because this slant is important. Over here we could treat this as if it were a straight line and just treat this as if it were a cylinder. But here this slant is important because of the shape that it makes. So we can't define it like just treat it as a straight line as we did over here. So we're going to define this slant here as ds. And we don't really know what ds is yet. But we're gonna put out our initial integral with the information we have here. So drawing this integral, we're gonna have the same bounds as our previous one. The integral from 1 to infinity of a times b. We defined a as 2 pi times 1 over x, and b, a times b, and b is equivalent to ds. That's what we've defined here. So what is this ds length that we're multiplying by? So if we were to take this cross section of our cone here, we see that ds is a slanted line. And if I were to extrapolate this slanted line, it would have x and y components. So this slanted line, we're going to make a triangle here. Our y components here, and our x components here on the bottom. So on this triangle here, this long length here is our ds, our x component is our dx, and our y component is our dy. And these just represent very tiny changes in these directions. That's just as if you were integrating. This is a very tiny change in the y, tiny change in the x, which yields our change in the y and the x congruently in the form of ds. So through the Pythagorean theorem, we can get a value for ds in terms of x and y. So we know that ds squared equals dx squared plus dy squared through the Pythagorean theorem. We just need ds. So we're going to take the square root of both sides, and this will leave us with ds equals the square root of dx squared plus dy squared. This isn't particularly useful to us yet because we need in terms of dx. So the following step, there's mathematical proof behind it, and through limits you can prove that what I'm about to do does work. So just for the sake of time, I'm essentially going to factor out this dx from underneath this radical here. So we're going to get that ds is equal to the square root of 1, because I factored out this dx, 1 plus dy over dx squared times dx. So now we have this problem here, and we have dy dx. Well, we can get dy dx because we know that our initial y function y was equal to 1 over x. And if we differentiate this function with respect to x, so dy over dx is just going to give us negative 1 over x squared. So we substitute this 1 over x squared, negative 1 over x squared, which are dy dx, from our initial function. We're going to substitute this back into underneath the radical here, square it, and then we're going to have 1 plus dy dx squared dx is our ds value. So we're going to substitute this back into this integral, and we're going to draw a new integral. So our final integral looks like this. The integral from 1 to infinity, and we're going to remove, just like we did over there, we're going to remove this 2 pi because it is a constant. 2 pi times the integral from 1 to infinity of 1 over x. And then remember, we had ds here, but we now know that ds equals this value. We're going to plug this into dy dx here. So we're going to get the square root of 1 plus 1 over x to the 4th, because we squared this here because we had this square, so we're going to square negative 1 over x squared, and we're going to get 1 over x to the 4th dx. So this is what we need here. However, this is an atrocious integral to work out. We could work this out through trig substitution, but I don't have the patience nor the paper to work that out here. So we already suspect, because of the nature of this paradox, that our surface area is going to be approaching infinity. We think it's infinity. So if we can just prove that some of this integral is infinity, if we can prove that without this part of the integral is larger than infinity, then with another part, it would be larger than infinity, yet still infinity. So this whole part here, this square root of 1 plus 1 over x to the 4th, we know that we're going to be plugging in x values from 1 to infinity, anywhere in between there. So if we start with 1, we're going to have the square root of 1 plus 1 over 1, so we're going to have the square root of 2. So larger than 1. As we get closer to infinity, this number gets closer and closer to 0, but never negative. So we'll always have at least the square root of 1 here, no matter what this x value, how high this x value climbs. So we can essentially say that this will always be at least 1. And so therefore it will not impact the value that we get from here, and can only make it larger. So we're going to rewrite this integral and just remove this, because we know that it will never subtract from our value, it can only add to it. We're going to get a much simpler integral. So this final integral is 2 pi times the integral from 1 to infinity of 1 over x dx. When we evaluate this integral, we find that we get 2 pi times the natural log of x evaluated from 1 to infinity. Well, the natural log of infinity is infinity. Multiply 2 times 2 pi, larger infinity. So we're going to have infinity minus an arbitrary finite value, which proves that our surface area is equal to infinity. We have an infinite surface area for a shape that we have already proven has a finite volume. which is truly mind-blowing how that could work. And I mean, that's why it's called a paradox, because you can't comprehend how that would work. So now what I'm going to do is show you a real-life model of Gabriel's horn. It was tough to make an infinitely long model, but as you'll see, I did manage to do that. And we're going to run an experiment where we try to fill the horn, and then I'm going to try to paint the outside of the horn, which certainly feels like an impossible task to me. Maybe not so much the filling of the horn, but the painting of the horn doesn't seem like we're going to get much done there. So let's check that out. So here we have our physical model of Gabriel's horn. I'll try to show it to you here.
One eternity later.
I can run as much as I want to, but I cannot physically show you the other end of this horn because it is infinitely long. So you just have to take my word for it. This horn just goes on forever and ever. But here I am holding it. It is infinitely long. Here's the top of that same horn. It's still infinitely long down. I drilled a hole all the way to the center of the earth, and it's poking all the way through that. So it's still there. I'm just able to hold it here to demonstrate. Now, the whole idea behind the painter's paradox is that this horn has finite volume but infinite surface area. So just to prove to you that it does have a finite volume, I'm going to fill it. You might be asking yourself, that looks like a Diet Coke bottle. You're wrong. Happens to be a bottle of exactly pi units of paint. And I will now show that pi units of paint fills this cone entirely. The infinitely long cone will be filled by this bottle. No tricks here. This will fill the entire horn. As you can see, completely full. This horn is full. There's no room for anything else in this horn. All it took was pi units of paint. Now, with the exact same horn that you just saw me fill up with pi units of paint, I'll now try to paint the entire outside of this horn. And I'll come back after I'm done. Okay, I'm back. I've been trying to paint this thing for 3 nights. I haven't slept. My hair's a wreck. I haven't even put a dent on painting this thing. Like, you can't even see what I painted. That's how much surface area this cone has. No matter how much paint, I tried to start with the same pi units of paint that I used to fill the horn, and it didn't even cover a little bit of the cone of the horn. So yeah, that backs up what we found earlier, that the volume of this horn is easily fillable by pi units of paint. But no matter how hard you try or how much paint you think you have, how much time you think you have, you will never paint the outside of this horn. I've tried, and just take my word for it, it's impossible, because the outside of this horn is infinitely large. When compared to the inside, which is finite, easily fillable, outside, impossible to ever cover. Thank you, and I hope you enjoyed this video, and I hope you learned something. I hope you enjoy this mathematical concept as much as I do. I think it's one of the cooler things that we learn in calculus. Thank you for your time watching it.